Next, we're going to use this opportunity to show you how we run the matrix multiplication example. Let's look at this matrix multiplication example. We have a couple of source code files under this matrix multiplication folder. Main.c is the host side program. MyKernel.cl is the kernel program. And we have a makefile to help us compile the project. Let's look at the host side program. This is main.c. As we see, it's a C program essentially with these header inclusions to include the standard libraries. And then we have a macro definition _apple __, and this includes some of the header files that are specific to the OpenCL framework on the Mac OS. And if we are using FPGA, specifically the Altera FPGA, and we're going to have to include different folders, different header files. And also on the FPGA side, Altera OpenCL framework supports C++ binders, so we can use namespaces and also use some of the functions in the OpenCL utilities implemented on the FPGA. And we also need to declare a cleanup function, which is part of the required helper functions on the Altera OpenCL side to help us clean up the framework. And then we have definitions for the device name. We have an array with a certain number of characters defined. Now here A and B, we have two floating point arrays. These are the two input matrices we're going to use for calculation. This matrix A is a 2x4 matrix. It has 2 rows, 4 columns. And the initial value in this matrix A is 1.0, or floating point. For matrix B, we have a 24 elements, so this is a 4x6 matrix. It has 4 rows and 6 columns. And so as you can imagine that the resulting matrix C will be a 2-row, 6-column matrix. In the main program, we start with a list of variable declarations for the number of platforms, the array for storing platform identifiers, and device ID and number of devices, and also the return value. We also declare CL context, so we can use this context to encapsulate all the objects in the OpenCL framework. We have the command queue declared, the OpenCL program, and OpenCL kernel declared here. This file pointer is what we use to open the kernel source code, and we give a fixed name, which is the mykernel.cl in the current directory. So we'll use the fopen function to read the kernel source code from this .cl file and then to compile it at runtime. And then we describe the sizes of these input matrices. So for the matrix A, the width is 4, height is 2. Essentially, this is the number of rows, and this 4 is the number of columns. Similarly, for the matrix B, we have width of 6, height of B, so it's a 4x6 matrix. The size of the resulting matrix C, the width of C is the same as the width of B, and the height of C is the same as the height of matrix A. So these are the variable declarations. Now, what we are seeing here in this part of the source code is where we get the platform IDs and also get the device IDs. Let's look at the case on Mac OS, which supports OpenCL native. We can first call this get platform ID give 1 as the number of platforms we expect to have, and also the platform count is to return the number of platforms. Then we allocate the array to store the number of store the IDs of these platforms. Then we call this get platform ID the second time to obtain the actual platform IDs. These 3 lines seems a little bit redundant, but typically this is how it's done on the OpenCL. The next 2 lines are getting these device IDs using a chosen specific type. We can just say we want to have a default OpenCL device. The Mac OS by default the OpenCL device is a GPU device, and we can use this device ID to store the device ID descriptor, and also we can find out how many of such devices that are available on the Mac OS, and typically the 1. We can also query the information of this device. In this example, we query the name, and we can store the name into this character array, and then we'll print the name out. On Altera FPGA, it's a little bit different. We also list the code here. So we'll start with get platform ID, and then we'll allocate the space for storing these platform IDs, and then we're gonna use this find platform to make sure that we do have Intel FPGA OpenCL platform available on this host. And so this find platform is a utility function implemented by OpenCL, Altera OpenCL runtime. And if we do not find such a platform, we will have to report that, and then we'll terminate this program. Now, by this point, we find the Altera FPGA OpenCL device. We will try to get all the available OpenCL devices. And we're really talking about the devices in this OpenCL FPGA platform, so you can expect you're going to get 1 or more FPGA devices. We'll then print out the platform name. We can also print out the number of devices we are able to find on this platform. And we will say we want to use 1 OpenCL device on this platform, and that is the FPGA device. You can double check by print out the device name, which will show you what kind of FPGA boards it has on this platform. Currently, this host side source code supports both Mac OS and also our OpenCL SDK by Altera. If it is running on a different platform, and they will, the program will report an error. Now we queried the platform and also find out the devices. The next step is to create OpenCL context. We'll call OCL create context. We will use the device IDs. In our case, we are using 1 device, and you can use multiple devices. And the return value will be the context object. Also, you have to sometimes check this return value to make sure this create context is not having any problems. On top of this context, you can create command queues. Each device can have a command queue associated with the device. So this API CL create command queue, you take context and device ID as the arguments to create this command queue. Next step is to compile the OpenCL program. Now I want to first show you on the Mac OS platform, which typically has a GPU, and how we're going to load the source code and then compile the program. So we will use fopen to open the kernel source code file. We already gave the file name mykernel.cl. So we're going to open that, and we will read the source code from the file, and then read all the characters and put them into this source str, this array, which holds all the characters in the OpenCL source code. I mean OpenCL kernel source code. And then we're going to close that file handler. Now the next step is to create kernel program object from the source. So we'll call CL create program with source. So we'll use the current context. We will use the buffer that stores the kernel source code, and we will then return a program object. This program object will be used later to create the actual kernels. Up to this point, we see how we can create a program object on Mac OS, which has native support to OpenCL. Now, in the next few lines, we're going to show you that the way to create such a program object is different on the Altera FPGA OpenCL SDK. What we see here is on the Altera SDK, we will need to create the object from binary. We mentioned earlier that to compile the FPGA using the FPGA design flow, it takes tens of minutes or hours to build a binary image. And this is also true for compiling a binary from OpenCL to a FPGA binary. So what we do is we will compile the kernel using SDK from Altera OpenCL SDK, and we will now, on the host side, we'll use the binary result from that compilation to generate this program object. So what we see here is we will use Altera specific API called get board binary file using the name of the kernel, and we will also specify the device ID so that they can check whether this binary is indeed designed for the device. And we'll show that we're using the kernel binary, which typically has a .aocx as the suffix in the name. And then we'll say create program from binary, use the context, and use the binary file, and we'll also supply the device ID. So as you can see, it's a little bit different how you compile, how you generate the program object on these two different platforms. After that, for either platform, we will proceed to build the kernel program. So we'll call this CL build program, which will take in the program object created from either the source or the binary, depends on the platform you use. We'll also supply the device ID. And here we check whether this build program is successful or not. And after that, we will eventually now create the kernel program. This kernel object is built based on the program object. In here, we are simply selecting a particular kernel function from that program object. And the reason behind it is in that program object, in the mykernel.cl, you may have multiple kernel functions. So here you use the specific kernel name to select the function. So up to this point, we have created the context, created the command queue object, also we created the program object, and now we have the kernel object ready. So in the next section of the program, we will see these buffer management. This is on the host side. we will allocate a buffer to store the resulting matrix C, and we know the size, so we can allocate that size of array storing these floating point numbers. The next section here, this is what we have saw in the lecture slides. We essentially create the buffers on the device side. We use CL create buffer to create the buffer A, which is a read-only buffer on the device side, and we will copy the initial value of the matrix A into this buffer A, and we're using CL enqueue write buffer to do that. Similarly, we'll create buffer B and also initialize the content of this buffer B using CL enqueue write buffer. And after that, we will allocate space for matrix C on the device. Now, this is again what you have saw from the slides. This is what we have to do to set the kernel arguments. Remember, you need to choose the kernel and also set the proper index for the corresponding kernel arguments. You will supply the size of the argument and the actual value of this argument. And by value, we really mean that we're going to use the pointer to these variables so that we can pass in the proper buffer pointers and other type of arguments into the kernel. And here we are setting these global workgroup size and local workgroup size. You see a little bit differently. We choose 2 here instead of 16 is because we would like this to be also executable on the FPGAs, which has a smaller work item size, smaller workgroup size. And this CL enqueue ND range kernel, this is for actually instantiating the kernels. We'll pass in the command queue object, the kernel function, and we choose 2-dimension. There's no offset for the global work items. We'll supply the work group size for the global and local, and we don't have anything on the events. I added a note here. I found out that it's very important to check the return value of this CL enqueue ND range kernel. Typically, you assume that it will success. You assume that it will succeed. However, especially on FPGAs, there are certain occasions that you will have to check to make sure it actually succeeds. Otherwise, you will find out you are puzzled why the final results are incorrect. And this is why we have this error checking here. Once the kernel execution is completed, we will then read the results to the host memory. This is what we do. We use CL enqueue rebuffer. It takes arguments, the command queue, the output buffer, and also the size of the data you want to copy. And also this is the destination, and it's basically the buffer on the host side that we use to store the computation result. After that, you can then verify the results by printing them out. The next few lines are just for best practice. We're gonna free the resources allocated. On the host side, also we're gonna free the OpenCL resources that we have used. Now let's take a look at mykernel.cl. This is the simple multiplication kernel we have designed and we have discussed in our lecture notes. And the name is simple multiply. It takes 7 arguments, and we're gonna use get global ID to get the row number and column number. Then we're gonna perform the dot product operation to iterate through the width of A, basically to multiply the elements in the row vector of matrix A with the column vector in matrix B. Then we're going to store the results in the corresponding element in matrix C. Now let's build the main.c program and also the mykernel.cl program. Let me just clean up what we have built before. And to build this host side program and also the device side program, we just type make. It's pretty quick. So for the host side program, essentially you are compiling a main.c, a single C program file. And for the mykernel, you are actually using the GPU compiler to compile the mykernel.cl into a GPU binary. And the make file actually takes care of different versions of GPU binaries that you might use. So let's look at what we have. After build the program on both the host side and the device side, we now have a executable called main. Also, we have different binaries available for different GPU versions. To execute this, we can just simply type the name of the executable main. Okay, so we can see here the device that has been find from the OpenCL platform is this AMD Radeon Pro 575 compute engine. And we're printing out the initial value of the C matrix C and the final results after the matrix multiplication, where this matrix C has 8.0 in all the elements inside this matrix.